So in this last lesson of statistics, we're going to be talking about making inferences from experiments rather than from sample surveys. So the big difference is we've conducted, or someone's conducted, a randomized comparative experiment with a control group and a treatment group. So we actually have data from an experiment that we ran, and now we're going to do some statistical analysis on it to come up with conclusions or inferences about the situation, about that treatment. But the calculations we do could vary from case to case. So if you look at this first example, if you just jump down to part A, you'll notice we're finding means, and we're going to be making conclusions based on the mean. Does it always have to be a mean calculation? No. We can calculate standard deviation, we can calculate mode, we can calculate some fancier regression line or things like that, and then make inferences from there. Okay, so today really we're just going to look at a couple examples of how we can make these conclusions or inferences from given experimental data. So if you look at A, we're going to find the mean yield of the control group. So what this is asking you for is basically the mean, which is your average. And we want the average of the control group. So what you're going to do is you're just going to go ahead and add up the control group, right? So that 1.2 plus 1.3 and so on, divided by the total. We have 10 plants. So we'll take the sum divided by the total of the control to get the mean of the control group. So hopefully calculating mean, no problem now. We're just adding it all up, dividing by 10, so we get 1.37. But notice that was for the control group. We want to compare it then to the treatment group. So we've done something to this other set of cherry tomato plants, right? We've added the soil supplement and we want to think, okay, well, let's take a look at the mean there. And then what we'll do is we'll do some analysis on that. So now we want to find the mean of the treatment group. So we're going to follow the same method, right? Add up all the treatment group yields and divide by 10. So we should get 1.69 for the mean of our treatment group. So what we can do from here is, one thing we can do is we can look at the experimental difference of the means, which is just taking away the treatment mean from the control mean, and just taking a look at what that difference is. So we'll just do that 1.69 minus 1.37 to get 0.32. Okay. And maybe we even want to visualize this. So we can draw a dot plot. Again, does it have to be a dot plot? No, it all depends on what you're trying to study. So here we're doing what's called a double dot plot, which is just one dot plot on top of the other. So we can kind of, it's not a side by side, but a top and bottom kind of comparison to see if there's a difference in the shape. But in this case, what we might want to be doing is we want to look at each individual plant, because there's only 10 plants each, which isn't a lot. And we want to see, is the spread relatively the same? So this might help us visualize things like outliers, or is it relatively normal, or whatever. So that's what we can kind of do with the display. And often it is nice to have a visual of our data anyway. So you want to think about what an appropriate display would be. So I'm going to put the control on top, the treatment on the bottom, and I'm just going to make a dot plot. And because we want them on the same number line, since we're stacking one on top of the other, think about a good scale. Like, do you want to go by 0.1 or 0.2? Where do you want to start? Where do you want to end? So I'm going to go ahead and go by 0.1. Since it's a relatively small spread. So if you see, the treatment goes as low as 0.7 and goes all the way up to 2.0. So I might start at 0.7 and try to get myself all the way up to, let's see, the treatment group goes up to 2.4. So I probably want to go up to 2.4 or 2.5. So I'm going to break down my number lines in that way. And there we go. So I only need to label one of my number lines because, again, we're using the exact same scale, the exact same number line. That way we can actually compare them. And then what we want to do is we want to go through and make those dots for the dot plot. So we're just going to look at each and every one of the plants from the control group and then put dots above the appropriate number, right? And then we'll go through and do the same thing for the treatment group and its number line. So you can see this first yield for the control group is 1.2. So I'm going to find that 1.2 on my number line and then just draw a dot, right? And the next one's at 1.3. Then the next one's at 0.9. And you guys get the idea. So I'll go ahead and finish this and then show you the completed dot plot for the control group. So remember, if you have more than one of the same number, you just stack one on top of each other. Okay. So if you guys want to go ahead and pause and do that treatment group dot plot on your own, feel free to pause right now. Otherwise, keep watching and I'll just show you my treatment group dot plot using the same method I did with the control. And there you go. So you can look at this and it might look a little interesting. So you see a larger cluster on the treatment group, a little bit more toward the right, but not that crazily skewed toward that side of my dot plot. So what can we say from this? Well, they're both fairly symmetric, right? So if you look at it, they both kind of have a bigger cluster in the center, and they have a couple here and there toward the end, right? And it doesn't appear to have any crazy extreme values. And of course, you can go ahead and calculate the outliers. So like I said, don't feel limited to just doing one calculation. If you want to do 1.5 times ARQR and add that to Q1 and Q3 to see what your outliers are, you totally can. But just based on the spread of this dot plot, it doesn't appear to have any obvious outliers like, okay, whoa, that one plant didn't yield anything at all, right? So it doesn't look like it has any crazy outliers. So it does seem like, well, the mean is kind of a good measurement, because remember, the mean is it will be skewed if we have outliers. So if there's no outliers, the mean could be decently reliable. So it seems like the treatment is slightly more effective, right? Because it does look like there's a little more yield on the higher end. However, now let's look back at our test, right? Our experiment only dealt with 10 plants. Is 10 plants enough to give us the confidence to generalize this for all tomato plants? Probably not. So because it is a relatively small size, sample size in our experiment, that difference could have been by chance, right? So to make this more reliable, we want to have a larger, potentially more reliable, we could make a larger sample size, right? Or something like that. We'll talk more about that in a bit. But let me go ahead and just type out what I just said. All right, so there is basically a summary of what I just said. I forgot to mention in my earlier talk about the difference of the means, that differential. And that's basically saying, right, there's a 0.32 difference. So that average value went up for the treatment group by 0.32 kilograms. So there is that slight bump. So could it have been because of the treatment? Yeah, it totally could have been. But because our sample size is so small, we might want to take that result with a grain of salt. And we'll talk a little bit more about that with the next example. Okay, so go ahead and pause right here and do the first you try problem. And like before, we'll come back and check these answers after I go over the next example. So hit unpause whenever you're ready to move on. Okay, so let's move on. What could we do if we have a situation like this example when our sample size just isn't large enough for us to be confident in our inference? Well, what we can do is we can do this method called resampling. What is resampling? So maybe we spent all this time and effort on these 10 plants and we don't want to throw it all away just so we can make a larger sample size, or maybe we're limited with resources and we can't get a greenhouse that'll house 1,000 cherry tomato plants, or we don't have the manpower to monitor it all, or and all that. So what we can do is we can do this method called resampling. And one way to resample is basically take those two groups that we had before and repeatedly mix and match them, right? Make random new groups of control and treatment groups out of those original 20, the 10 control and 10 treatments. And then we'll just keep resampling over and over again and see what results we get. So again, we're not growing new plants every single time. We might take those 10 original controls, label it 1 through 10, the 10 original treatments, label it 11 through 20, and mix and match. So our new control will be something like 1, 2, 15, 17, 13. It's just going to be randomly chosen. So basically throwing all those numbers in hat again, picking 10 random ones to become control, and the other 10 will become treatment, and we'll run through the whole cycle again. And we can do that multiple times. And again, is there a set number we have to do? No. We have to do enough for us to feel our results are reliable, right? And if we can start seeing a pattern or a trend, then we can feel very, I wouldn't say very, but more confident, right? That we do know what's going on with the treatment. Is it actually effective or not? Okay. So clearly, right, we'll resample multiple times. And in this example, next, we decided to take a look at the hypothesis that the soil nutrient has no effects on the yield of the cherry tomato plants, and then resample the original two groups 200 times, right? Where'd they get the 200 from? I don't know, but 200 is a really large number. So after you do those 200 samples, maybe you're feeling like, okay, I did finally see a trend, or I didn't see a trend and I've already done so many, maybe there isn't any. So you might just have to keep going and look at your data until you feel like, okay, 150 to 200 still giving me the same type of results. I'm feeling like it's pretty consistent. All right. But again, that total number is kind of up in the air depending on your experiment. So anyway, we had our experimental difference of 0.32 from the first example, and now let's look at the resampling differences. What can we conclude about the hypothesis? Does the soil nutrient actually have an effect on yield? If our hypothesis was it doesn't. So let's first start by looking at what the hypothesis assumes. If it has no effect on the yield of the cherry tomato plants, then that would mean the average or the mean for the control and the treatment should be pretty much the same. There should be no difference. So if we keep that in mind, we can see from our histogram on the left here that if the assumption is the difference is 0, we're right here, right? Oops. At this bar. Okay, so now let's take a look at where the experimental difference of 0.32 from our earlier experiment, from that first example, lies. Well, that's way over here at that line here on our histogram. So let's try to interpret this, okay? Because we don't have our exact numbers. We don't know exactly how many had a mean difference of 0.32 and how many had exactly 0. We just kind of have this spread. So 0, the number of times they hit 0 somewhere in that 29, the bar with 29, right? The 0.32 somewhere in that group of 5. We don't know exactly how many. So let's do our interpretations as best as we can. So if we think about this, we have a resampling size of 200. So if I'm like thinking about, okay, the bulk of the data, let's say 90% of the data, 90% of 200 is 180, right? 0.9 times 200 is 180. So if I'm looking, where is 180 data points or 180 of my resampling? Where does that lie? Well, that lies between here and there. So this is 90% of my data. So the majority of the resampling doesn't actually include that 0.32. Does that make sense? So that 0.32, that bar, doesn't lie within the 90%, which means it's kind of out there. If you add them up, right, these last 3 bars equal 10. Ooh, that's a really thick pen there. Let me just kind of redo that. So if you add up these last 4 bars, that's 10. That means at most, right, 10 of those resamplings were bigger than 32, at most, which means there could be no more than 5% of the values that would have been, you know, larger than 0.32. So what is this saying? If you go back and remember what we talked about with creating hypotheses, this is saying it's highly unlikely for us to get that result if the hypothesis is true. So what this is telling us is there is a suggestion here, because this is unlikely to happen if the difference between the yields is 0, then it's suggesting that the treatment group and the control group do differ, right? It means that the difference of the means wouldn't actually be 0. So what's interesting about this is then we can say, okay, well, that hypothesis we pose that the yield has there's no effect on yield if we do a treatment to the cherry tomato plants is actually false. So there is some effect on the yield with the treatment, right? And since that mean value or the mean yield difference that we got was positive, it would be increasing the yield. All right, we can't say anything more concrete from that, like what percentage and whatnot, because that's not what our data is telling us, but that's something that you could do as an extension to the study. You're like, okay, it is highly likely that this treatment is going to increase our yield. Let's dive into this some more and figure out exactly what percent it's increasing, right? So that's where you can keep growing your experiments. So let me go ahead and write down everything I mentioned, and then we'll move on. All right, so that kind of summarizes what I was saying. So basically, we were able to conclude that the hypothesis is likely false because it's highly unlikely that we would get 0.32 by chance if that hypothesis was true, which then tells us that the treatment likely does help the yield, and because 0.32 is positive, it's likely to increase that yield. So feel free to pause if you want to write all that down. And also, once you're done, move on to that last U-try, and then hit unpause when you're ready to check the 2 U-try problems. Okay, so jumping up to those first U-try problems, and you'll have hopefully noticed that the U-tries today aren't separate problems, but basically just kind of diving into the interpretation, because really we're using our knowledge from before and how we can interpret our data to come up with inferences, to come up with some kind of conclusion. So for the U-try for this first one, I was asking you, what if the difference ended up being negative or 0 or positive, like the one we saw in the first example, that 0.32? What does that tell you? So the negative mean yield difference means that there is an effect, and that effect is the opposite of what we would have wanted, right? It's making our yield smaller. It's somehow not letting as many cherry tomatoes grow. The 0, which I actually mentioned in that second example, means there's no difference at all. You could have not done the treatment or done the treatment, it made no difference, right? And positive, what we said with that 0.32 is actually increasing the yield. There it does have an effect. Okay, and that second you try problem, again, wasn't a brand new problem, but asking you for a different interpretation. So what happens if we made a mistake and we concluded the hypothesis is false when it's actually true? So we have to think about the ramifications and repercussions of what we do, and that's why we really, really want to be as accurate as possible with our inferences and our conclusions. So if we were wrong by accident in this case, we could have somehow given consumers confidence that they should go out and buy this product when it actually does absolutely nothing for us. And then we've just ask people to go out and waste their money on a treatment that's ineffective, right? So that's something to really think about, why we want to be very careful, very precise and accurate when we are making inferences. And then you'll be practicing this. So definitely ask if you do have questions about the analysis of the numbers to help lead us to inferences. Okay, thanks for listening.